This tutorial will start by running the pre-built genetic algorithm, simple robotics, Java 8 application. And second, I will use the generated output in order to quickly explain what this application does. And third, I will step by step write and explain the code using an Eclipse IDE. This is a pre-built application, so let me go ahead and run it. So given those route coordinates, we are using genetic algorithm in order to evolve a solution that lets a robot autonomously navigate from begin and go through the different route until it reaches the end. And for simplicity, the robot here has only 4 detectors. So backward, right, left, and forward. And each one of those can be either 0 or 1 depending on what it detects. Meaning if it detects a route, then it is 0, and if it detects a wall, then it's 1. And the robot can perform one of 4 actions. It can do nothing, and this we represent that as 0 0, and it can move forward, and we represent that as 0 1. So here it's moving forward from position 0 0 to position 1 0, and it can turn clockwise, and we represent that as 1 0. So here the robot in position 1 0 turns clockwise, and it can turn counterclockwise, and we represent that as 1 1. And the combination of detectors, we represent that as an integer. So for example, this is 13 as an integer, this is 14 as an integer, and this is 3 as an integer. So this is 3 here, and for this combination of detectors, this is the action that is taken. 1 0 meaning turn clockwise, and for example here for 14 we have 0 1, which is move forward. And the robot direction is from the point of view of the robot itself. So if we are in this direction, so backward, right, left, and forward, and if the robot turns clockwise, then it goes into this direction, and here if it turns clockwise it goes into this direction, and same thing if it turns clockwise it goes into this direction, and if it turns counterclockwise it goes into this, and this counterclockwise goes into this, and 2 counterclockwise goes into 1, and 1 counterclockwise becomes 4. So initially the robot is in this position. So forward has a wall, so to overcome that it turns counterclockwise, and now it is in position 4. So forward is this way, so it goes ahead and moves forward, and here in position 1 0 it turns clockwise, so forward is downward. Now we're in this position, so it can move to position 1 1. So 1 0 move forward, we go into 1 1, and we keep going 1 1, we move forward to go here, etc. So this fittest solution, we evolved it from here, from generation 0, and this is the population of potential solutions, and this is the fitness for each solution, and they are sorted by fitness. So we start from this generation, and after 250 generations we end up with this fittest solution that we are printing over here, and this is what allowed the robot to go from begin to end, so from position 0 0 to position 0 5. I will start by creating a new project, and this will be running on Java 8, and here I will have a driver class with a main method, and it will be in this package, and this will be the driver for the whole application, and a solution class, and this represents the action that the robot would take when faced with each set of detectors, and a population class, and this represents a population of potential solutions, and a genetic algorithm class where selection, crossover, mutation, and elitism will be implemented. And next I'll have a route class that will be in this package, and this represents the path that an autonomous robot navigator would be traversing, and I will refer to the beginning of the path. So this is 1, the end of the path is 3, and a wall is represented by a 0, and a route that to be traversed is represented by 2. And let's take this as a potential route coordinates. So we start from begin and we end with end here, and the robot would be traversing all those routes. And this class will only have one method, get route position value, and since we're using position here, let's go ahead and define that class. So it represents an XY position in the route, so we have x and y, and they are initialized in the constructor. And we'll have another constructor that instantiates a new position instance given a pre-existing position. And let's have get and set methods for those x and y coordinates, and a toString method that returns those coordinates in this format, as a string in this format. So let's go back to the route class, and let's have a return value that will be initially returning 0, a wall, and return that return value. And if the x and y coordinates are valid, here we're checking for that, then the return value will be the coordinates. So route.coordinates, and this is position get y and position.get x. So we either return a wall, meaning 0, or we return begin or end or route, given the position and the coordinates. So begin here is 0, 0 coordinates, route is 1, 0, etc. And the last class we will be creating here is the navigator class, which represents an autonomous robot navigator, and the directions from the point of view of that robot would be either backward or left or forward or right. And the moves that it can take are either it can do nothing, this is represented by a 0, or move forward, which is represented by a 1, or turn clockwise, or turn counterclockwise. And next, let's go to the solution class, and I'll define this number of digits to be 32. And the reason this is that we have 4 detectors, so we have 16 possible set of detectors, so we represent those here from 0 to 15, we represent them as integers. And we had here 4 actions that are possible, that do nothing, move forward, turn clockwise, and turn counterclockwise. And we represent those as 0, 0 for 0, and 0, 1 for 1, and 1, 0 for 2, and 1, 1 for 3. So we need 2 digits to represent those 4 possibilities. So here we have 2 digits for each possible set of detectors, and we have 16 times 2 gives us 32. So this is the number of digits being 32. And let me define this array list that would have those 32 digits. So each one of those. And the solution will have a fitness. So let me initially define this fitness and set it to -1, and I'll define a Boolean fitness flag and set it initially to false. And I need a get digits method that would return this array list of digits. And I will have a constructor that will instantiate this array list given the number of digits, and initialize it initially with nulls, and then populate it with zeros or 1 randomly. And I need a method that calculates the fitness for a solution, and for now let's return 0. And the get fitness method will check the fitness flag that we defined over here, and if it is false, then we recalculate the fitness. Otherwise, we return the fitness that we already have. And here each 2 digits represent an action, so we need a method that would return those actions. So I'll have this get actions method, and the number of actions is essentially the digits size over 2, since each 2 would make an action. And let's instantiate the array list to be returned given the number of actions. And return it. But before doing that, let's add the various integer actions here. So we end up with 16 possible actions in the array list that is returned. And I need a toString method that would print this as a for each solution instance. So we are adding this between each 2 digits that represent an action, and returning this string. And before writing the calculate fitness method, let's go to the navigator, and so the navigator will have one public method, which would be activate, and let's return null for now. So given an array list of actions, of 16 actions, we return an array list of positions that this autonomous robot navigator will be taking, or will be moving through. So let me go back to the solution class, and here in calculate fitness we will be calling navigator. So a new instance of navigator will be calling activate method on it and passing in the actions, calling the get actions method that would return the actions for this solution instance. And before recalculating the fitness, I'll set the existing fitness to 0 and instantiate an isVisited array list that keeps track of the visited positions. And let me here return the fitness, the calculated fitness. And before doing that, I'll set the fitness flag to true. And for each position here, I'll check that it's not already visited. And if that position is a route position, then I'll add 1 to the fitness and make it as a visited position. So this should do it for this class. And next we'll be doing the population class. Here we will have an array list of potential solutions. And a get method that would return those solutions, and a sort method that would sort those solutions by fitness, and it's using Java 8, and it would return a sorted array list of solutions. And I will have a constructor that takes in a population size, and based on that we will instantiate an array list of solutions. And populated with new random solutions. So this should do it for this class. And an example population is here. Let's say this is a generation that we are in, and those are the detectors as integers, and this is the sorted array list of potential solutions, and they are sorted by fitness. Notice the highest fitness is first. Next, let's go to the genetic algorithm class, and here I will have a private method that does population crossover, and for now I'll return null, and another private method that does population mutation, and for now I'll also return null. And the only public method that we will have in this class is this evolve method that takes in a population and ends up calling crossover population, and the population that is returned from that, it calls a mutate population on it, and returns the evolved population. And crossover here is using tournament selection. So we will end up using this method, and for now let's just return null. And we will have this private crossover solution method that does crossover on those two solutions, and for now let's just return null. And the mutate population will end up making calls on this mutate solution method, and let's return the mutated solution here. And before proceeding here, let's go to the driver class and define those constants. So the maximum number of generations, let's say it's 250, and the population size, say it's 10 potential solutions, and the mutation rate, and the crossover rate, and the number of elite solutions, and the tournament selection size, let's say it's 4. And we only have one solution that get passed as is from one generation to the next. And now let's go back to the genetic algorithm class, and in crossover population, first thing we want to do is to make sure the population passed in is sorted. So sort by fitness, and let's instantiate a new population that we want to return. So crossover population based on the solution, so populations that get solutions that size of the passed in population, and we will be returning this crossover population. But before doing that, we will pick the elite solutions and set them as is in this new crossover population to be returned. And as we just mentioned, we only have one solution that is elite here, since this is one, the number of elite solutions. As for the remaining solutions to be populated in this crossover population, we start from 1 here, from the number of elite solutions, and we go to the size of how many solutions we have in the passed in population. So we pick solution 1 is we do population dot get solutions dot get a solution from there, and then for solution 2 we do select tournament population, and we pick the fittest solution from that population that is returned here, and then we call crossover population, or actually I meant to say we call crossover solution on solution 1 and solution 2, and we set what is returned here in crossover population. Now in mutate population, so initially we do pretty much the same as we did in crossover population. So we sort the passed in population, and then we instantiate a new population. We call it mutate population, and this mutated population will be the one that we will be returning, and we pass the elite solutions as is to the new mutated population. As for the remaining solutions to populate this mutate population, we start from the number of elite solutions, so from 1 here, and we go to the size of the solutions that we have, and we end up calling a mutate solution on each one of those solutions. And we set the returned solution and this mutate population that we end up returning. Now for crossover solution, you will instantiate this crossover solution and end up returning it. But before doing that, we'll check the crossover rate. If it's bigger than a random number, then we perform the crossover. Otherwise, crossover solution is gonna equal to solution 1. It's passed in here. So here I'll pick up a random swap position. I'm using mass.random here, and depending on where we are with respect to that random swap position, we'll pick up from solution 1 or from solution 2. And for mutate solution, then we will go through each digit in the digits array list and check if the mutation rate is bigger than a random number, and we would flip the bits here and return the mutated solution. And what remains here is this method. So we will have this tournament population that we would instantiate based on the tournament selection size, which here we have it to be 4 in this case. So we will be returning a sorted tournament population, sorted by fitness. And before doing the return, I will randomly populate this tournament population with 4 random solutions from the passed in population. So this should do it for this class. Next, let's write the code for the autonomous robot or the navigator class. So here we only have one public method, activate, and we will have several private methods. So one of them is step forward, when the navigator needs to step forward, and change direction when it needs to turn clockwise or counterclockwise. And we need a method that would return a set of detectors as an integer. So let's for now just return 0. And this method will end up calling this other private method, calculate detectors as integer. So let's define the max number of moves that this robot can take, and let's say it's 50, and this counter keeps track of the number of moves that the robot have already taken. And in the activate method, let's say we have a continue flag that we start with true, and we will pick up the solution action. So here we're passing the actions for a solution. So we have a specific solution action based on the state of the detectors, and we pick up those as an integer. And I would increase the number of moves of the robot, and let's have here an instance variable, a route instance variable, and a current route position, and we start from position 0, 0. So if we are not at the end of the route, and if we haven't exceeded the maximum number of moves, then we do a switch statement on the solution action, and this can be one of those four things: a do nothing, move forward, turn clockwise, and turn counterclockwise. And let me define a route string as an array list, and a route positions. So with the route positions, we are keeping track of the positions on the route, but the route string is for display purposes. So initially I will add these to the route string: the position, the detectors, and the detectors as integer, and the action. And let me define here the direction, and it will be initially direction forward from here, and detector as integer instance variable, and I'll set it initially to -1. So now here in this switch statement, I'll have the case where the action is do nothing, meaning 0, 0, or move forward 0, 1, or turn clockwise 1, 0, or turn counterclockwise 1, 1. And in case it's do nothing, I'll set the continue flag to false. In case it's move forward, I'll call step forward, passing in the current route position. And in case it's turn clockwise, I'll call change direction and pass it the turn direction. And same for turn counterclockwise. And I'm adding here to the route string what is to be displayed. And I'll reset the detectors as integer to -1. And if we have reached the route end, or if we have exceeded the max number of moves, I'll go ahead and set the continue flag to false. and this will be returning the route positions array list that we defined over here. And initially in the constructor I added the current route position, which was 0, 0, 0, position 0, 0. And for the step forward method, this would be the code, and here we stay in the same position if we hit a wall. Otherwise we add a new position for current position to the route positions array list. So if we are stepping forward and the direction is backward, then we do current position dot get y minus 1. If it is forward, then we do current position dot get y plus 1, and if that direction is left, we do current position dot set x, current position dot get x plus 1, and if it is right, we do current position dot set x, current position dot get x minus 1. Now in case we need to change direction, this is the code that would do that. So if the current direction is backward, and if the turn direction is turned clockwise, then the new direction will be direction dot left. Otherwise, if the turn direction is turned counterclockwise, then the new direction will be direction dot right. And same concept for forward, left, and right. And for get route current position detectors as integer, this will be the code that does that. And this will call calculate detectors as integer, so this method, which will have this code. And the logic of how we came up with here 1 and 2 and 4 and 8 is over here. So for example, we have 8 here. So for the next 8, we start 0, we add 8, 1 we add 8, and 2 we add 8, and then 3 we add 8, etc. 7 we add 8, and so we end up adding those, which give us this, which would be 15, and here which would be 14, 13, etc. And same concept here, we have 4. So for the next 4, we start from 0, we add 4, 1 we add 4, 2 we add 4, 3 we add 4. So this plus 4 and plus 4 plus 4 and plus 4 gives us this, which would be 7, 6, 5 and 4. And same for 2, so we have those 2, and the next 2 we add 2, 0 we add 2, and 1 we add 2. So this is how we come up with a number from 0 to 15, given 4 different detectors. And the detector is detecting if there is a wall or there is no wall, 0 or 1. Actually, if there is a wall, it's 1, and otherwise if it is 0. And here the string here is for display purposes, and the route string. So here we pick up the front position, left position, right position, and back position depending on what the direction is, and we pass it to the calculate detectors as integer, which would return, or actually it would set the detector as integer that we defined over here. So this should do it for this class. Next, let's do the driver class. So let's start by picking up a new instance of driver, and we will start from generation 0, and I will instantiate a genetic algorithm and a population, given the population size, which is 10, and I will calculate the fitness for each solution in the population, and then sort the population by fitness, and I will have this method that just print out the population, and we'll call it from here for generation 0. So let's test run this application before finishing up the code. So generation 0, and those are the detectors as integers, so 16 possibilities, and this is each one of the potential solutions with the fitness for each. So this one has the highest fitness. Next, let's go ahead and evolve the population. So I'll have a while loop while we're smaller or equal to the max number of generations, which we defined here to be 250 generations. I will first go ahead and evolve the population, and then calculate the fitness for each solution in the population of solutions, and then sort the population by fitness, and print out that population. So let's go ahead and test run it again before finishing up the remaining code. So here we go, we went to generation 250, and we started from generation 0. So this was the fittest solution here, and this is the fittest solution here. And let me add another method that does printing. So print the fittest solution, and here I'll pick up the fittest solution for the last generation, and then print it. So let's run it again before adding more code. So here we go. This was the fittest solution. So we printed it out here. Those are the detectors as integers, and those are the actions for each set of detectors. And if we come back here, I'll add 3 methods that also does printing. So print route map details. All what it does is it prints out this route coordinates that we defined here, and this is just for display purposes. And this will print what the robot is doing, and this would print the directions basically when the robot changes direction. So from the point of view of the robot, if we are in this position and we turn clockwise, then we end up in this position, etc. 2 turn clockwise, we end up in 3. 3 turn clockwise, we end up with 4. And 4 turn clockwise, we end up with 1. And 4 turn counterclockwise, we end up with 3. 3 turn counterclockwise, we end up with 2. And 2 turn counterclockwise, we end up with 1. And 1 turn counterclockwise, we end up with 4. So I will be calling those 3 methods from here. And now let's go ahead and test run the application, the finished application. So here we go. This is the fittest solution, and those are the route coordinates, and this is the robot navigate route coordinates. So here we're position 0, 0, 0, 1, 1, 0. So this is 0, 0, and this is 0, 1, and this is 1, 0, and actually this is 1, 1, and this is 1, 0. So here the different position and what the robot is doing. Here it's turning counterclockwise, and then it's moving forward, so it's position 0, 0, and then 0, 0 it moves forward, and then it turns clockwise, move forward, etc. until it reaches position 0, 5, which is here, the end position.